continue on thinking about orthogonal vectors, so we're going to start out with a convenient bit of language. We say that v1, v2 through vn is an orthogonal set of vectors if each of the vectors is non-zero and the dot product of any two vectors with different indices is 0. So first, we're going to show that an orthogonal set of vectors always possesses a nice property. That property is that an orthogonal set of vectors is always linearly independent. A constructive proof of this is tricky, so we're going to do a proof by contradiction. And we're going to suppose for a contradiction that we can write one of the vectors, vi, as a linear combination of the others. The first thing to notice is that this sum on the right-hand side does not contain vi. Because this is an orthogonal set of vectors, we know that when we take the dot product of vi with vj, when vj is not equal to vi, we'll get 0. So if we take the dot product of vi with itself, we can rewrite one of the vi's as the linear combination. We can distribute vi to each of these terms. And because we set up our linear combination to not include the vector vi in it, we know that each one of these dot products must be 0. Since we know that the dot product of vi with itself is the norm of vi squared, this tells us that the norm of vi is 0. But of course, the only vector that has length 0 is the 0 vector itself. So this tells us that vi must be the 0 vector. But of course, this can't be true. The reason for this is we assumed the vectors v1, v2, down to vn form an orthogonal set of vectors. And one of the conditions for being an orthogonal set of vectors is that each of the vectors is not 0. This is a contradiction. Because we assumed that vi was a linear combination of the other vectors from our orthogonal set, and that assumption led us to this contradiction, the initial assumption must have been false. This means there cannot be any linear dependence amongst our set of vectors. Since there is no linear dependence, that means that our vectors must be linearly independent. Now that we know an orthogonal set of vectors is always linearly independent, this makes it natural to think about an orthogonal basis. We know that a basis is a set of vectors that are linearly independent and which span the space they are in. So we define an orthogonal basis for an n-dimensional subspace V living inside of Rm to be an orthogonal set of n vectors. So while this might seem strange, this is actually relatively familiar. One familiar example is the standard basis for Rm. So if we take the standard basis E1, E2, and E3 for R3, then we can check that this is in fact an orthogonal basis. We can do this by simply taking the dot product of E1 with E2, E1 with E3, and E2 with E3. For a less trivial example, let's consider the two vectors U1 with coordinates 1, 1, and U2 with coordinates -1, 1. If we take the dot product of these two vectors, we'll see that we get -1 plus 1 is in fact 0. Since there are two vectors, they are linearly independent, they form a basis for R2, they are therefore an orthogonal basis for R2. So similar to the standard basis, an orthogonal basis is easier to work with than other bases. To see this, we note that we can always write a vector b with coordinates x and y as some linear combination a times u1 plus b times u2. And because this is a basis, this representation is unique. The fact that these vectors are orthogonal makes it easier to find out how to do it than with an arbitrary basis. To find A, we use the orthogonality. We compute u1 dotted with b, we distribute the dot product across the sum, and we note that u1 dot u2 is 0. So we can, of course, solve for A by simply dividing both sides by the non-zero number u1 dotted with u1, which is the norm of u1 squared. And we can use the same trick to find b. Simply take the dot product of u2 with b. And now, of course, you recognize that you've made a mistake because you wrote your notes in LaTeX and you wrote your slides by hand. So on my screen, there are two different types of B's. One of them is bolded and the other one is not. So to avoid confusion here, I'm going to put a little hat over my vector B. That way you know that one of these is a number and one of them is a vector. So to compute what these coefficients are explicitly, we're going to compute the dot product of u1 with the vector whose coordinates are x and y. This is going to give us x plus y over the square root of 2 squared is just 2. For the second coefficient, we'll do u2 dotted with the vector b, whose coordinates are x and y, divided by the norm of u2 squared, which in this case is also 2. So this tells us exactly how to express any vector in R2 with coordinates x and y as a linear combination of u1 and u2. Namely, x plus y over 2 is the u1 coordinate, and negative x plus y over 2 is the coordinate corresponding to u2. So explicitly, we can write the vector xy as x plus y over 2 times u1 plus y minus x over 2 times the vector u2. So for example, if we wanted to express the vector with xy coordinates 2 and minus 4 in terms of this new basis, we just have to plug in 2 for x, negative 4 for y, and then we're done. And in fact, this sort of trick works in general for any orthogonal basis. If v1, v2 down to vn is a set of orthogonal vectors, then every vector b in Rn can be expressed as b is equal to v1 dotted with b divided by the norm of v squared times v1 plus v2 dotted with b divided by the norm of v2 squared times v2 plus etc. plus vn dotted with b divided by the norm of vn squared multiplied by vn. And of course, because the orthogonal set of vectors is a basis, this representation is unique.